Hey everyone, welcome to take two of this video. And yes, it's take two because I made the whole thing and the sound was off, so I have to do it again. So sarcasm is going to be pretty high during this particular video. Well, that being said, the purpose of this video is to help you answer the question you probably always wondered. When you look at a periodic table, what the heck is that number? You learned in middle school that every atom has a number of protons, and that number is always represented on the periodic table in the box for every element. And it's a whole number. It's how many protons you have, so it's got to be a whole number. And then you've always been told this is a mass, and so we just usually call it the atomic mass. And you're like, gosh, why the heck is it not a whole number? Because I learned earlier that every atom has a mass number, which is the sum of protons plus neutrons. Well, these are just particles, so you would think the sum would just be a whole number. But it's not, and that's because this is an average. And not just any kind of average, it's a weighted average. So let's take a closer look at why that's true. Well, the answer goes back to how do we come up with how many particles we have. We all know that chlorine isn't all the same atom. We have chlorine 37, we have chlorine 35, and there are a couple others, but those are the main two for chlorine. So how do we know that? Where does it even come from? Well, a mass spectrometer is a useful piece of information. One of the things it can do for us is tell us about the abundances of each isotope, how much of each there are. So it kind of works like this. I don't want to get too in detail here, but into this port right here we would inject some chlorine gas. Any sample of chlorine is going to have a little bit of all the isotopes. A lot of 37s, a lot of 35s, and that's mostly it. Now what we do with those atoms is that we hit them hard with something like an X-ray, something very powerful that will energize the electrons enough that they leave the atom, and it forms chlorine cations, positive chlorine ions. Now we will pass those through the electric field here with a positive plate and a negative plate, and the positive charge will be accelerated toward the negative plate, and out they go. And then we get to the really important part of the mass spec. This is a magnetic field created by a very strong electromagnet. Electric charges are affected by magnetic fields, and it will bend. This is going to be a positive plate up here, and this is going to be a negative plate. So as I shoot these positive chlorine cations down the tube, they will be bent or deflected off of their course. Why are there different courses, you think? Well, to understand this requires a little bit of physics. So let's keep it simple and think about what you've experienced. Many of you have gone around curves in the road, and most of you have done it very quickly, and many of you have the fortune of doing it very quickly with different types of vehicles. From your experience, if you take a sharp curve in a lightweight car such as a Porsche or maybe a Mini Cooper or something very small, the car takes the curve very easily. Okay? But if you try to do the same action in a heavy vehicle like a large truck or a large SUV or a large van, the vehicle has a much more difficult time taking the curve because of inertia. The masses want to keep going in a straight line. So what we're doing here, the magnet is creating a force that's deflecting the particles from going into a straight line. And if they have different masses, like the chlorine 37 and the chlorine 35, they're going to bend at different angles. And at the end, at the detector down here, we'll see some dots spread out where the different isotopes are hitting. Bottom line is the mass spec allows us to separate the different isotopes of the chlorine. Here's an example of the results we get from a mass spectrometer. This is just a printout, and it's a graph of the different isotopes that we've already talked about on the x-axis. The z term here is the charge. This is called a mass to charge ratio, and for the purposes of this video, the charges are always going to be +1. In the real world they aren't, but for us they're going to be. Okay, so this is a sample of the graph data we get. So for all intents and purposes, the x-axis down here is mass. So 35 and a 37. On the y-axis is a percent abundance. It's a measure of how much of each of those isotopes we're going to get. So we can see here that the chlorine 35 is going to be about 75%. And the chlorine 37 is going to be about 25%. So they're unequal amounts in nature. Nature actually makes about 3 out of every 4 chlorine atoms be the chlorine 35 isotope. And then about 25% of them are the other isotope. So how does that affect the mass? Anytime we take the mass, we have to account for the fact that we have each of these different mass numbers of the chlorine atoms. So you're thinking, well, heck, if I have 35 plus 37, wouldn't the average just be 36? And the answer there is no, it wouldn't be, because they're not equally weighted. There's more of the 35 ones. So the average isn't going to be right in half. It needs to account for the fact that there are more of the 35 weighted atoms. So what we need to do is calculate what's called a weighted average. Let me write that word out, weighted average. You've been doing a weighted average your whole life, you just didn't know it. So the formula is to take the percent and multiply it times each mass that you're weighing in this case. So let's go back and let's assume that this was a 50-50, like the one you grew up. We just discussed the math behind this was 36. So let me backtrack you through this to prove that this weird-looking equation is the one you've known all along. Let's do a little algebra here. Let's factor out a 0.5, and we'll get 35 plus 37 here. And let's rewrite 0.5 as 1/2, and let's keep the 35 plus 37 here. And then let's just rewrite this 35 plus 37 over 2. Voila. There's the average formula that you would have done. But what you never learned in elementary school is that the condition for this average formula that you grew up using was that everything had to be equal weight. Everything had to count the same or have the same influence. And in the case of isotopes, that is clearly not the case. So we have to find the weighted average. For our problem here for chlorine, we've got 75% or 0.75 are the chlorine 35, and then the other 25% are the chlorine 37. So from the equation, do you see what's different? Instead of 0.5 and 0.5, I have the percent abundances that the mass spectrometer gave me. And we just do the math. We're going to use the calculator, 0.75 times 35, and then plus, and then 0.25 times 37, and then add those two together, you're going to get 35.45, which makes sense. It's in between 35 and 37, like any average should be, but it's not right in the middle at 36. It's weighted toward, it's closer to 35, which is more abundant. So that's how you find a weighted average. Let's go to a practice problem now and do it with a little bit longer problem. From the practice handout that you have, we kind of already went through problem number 1 with chlorine. So let's go to number 2 here where we have lead. Now this is kind of a long problem, so bear with me here. The most important thing for you to do, because students make this error the most common, is make sure you convert your percents to decimals accurately. Remember that this is just 1.4%, which in decimal form is 0.014. Most students would accidentally put 0.14. All right, and then this one is going to be 0.241. And then this one will be 0.221, and finally 0.524. So that's making sure you convert your percents to decimals accurately. Now, as far as finding the weighted average here for lead, we have 4 atomic masses, 4 abundances, so let's plug into our little equation. So 0.014 times the 203.97302, good grief, what a number. And then we're going to add to that the product of 0.241 times 205.9744, And then let's just come down here and start the next one, 0.221. What a bunch of numbers. And then 0.524 times the final thing here, 207.97. So there we go. So now it's just a matter of calculation. Plug these into your calculator, and you're going to come out with 207.2. Okay, and the unit this time would be AMU. And if you check your periodic table for lead, that's exactly the number you're going to see in the square for the atomic mass of lead. It's a weighted average. That's one reason that it's a decimal number, not a whole number. It's because we're not just adding them up, dividing by 2 or 3 or 4. We're adding them up, but first weighting the sums by their percent abundance. All right, real quick before we move on to the next problem, let's hit the clear button there and scroll up. And then this is just a little bit different approach to the type of problem we're working here. The atomic masses of lithium-6 and lithium-7 are 6.0151 AMUs and 7.0160. If the average atomic mass of lithium is 6.941, okay, so what this is telling you is this is the one on the periodic table. That's the average right there. And this problem wants us to calculate the percent abundance. So we're looking for the percents. Well, let's plug into the same equation. This time we're given the average, 0.6941, and that's going to equal our percents, which we don't know. So let's make lithium-6 X, and then we said its mass is 6.0151. Well, if lithium-6 is X, what the heck is lithium-7 going to be? There's only 2 of them, so their percents have to add up to 100%. So if one is X, then the other has to be 1 minus X. And then times the 7.01. Oh, having some trouble writing this one. 0160. Now we just have to solve for X using some algebra. So I just distribute all my numbers out and come up with an equation here. Now I just need to combine my X's and combine my numbers. So let's do that. I had a little technical snafu there, so I had to rewrite the problem. So I think this is where we left off before I had to hit pause on my recording. So I put all the numbers together, and then I put the X's terms together, and this is where we were. So now if I want to solve for X, I'll divide both sides by the negative 1.009. Negative 1.009. Oops, left the 0 off. And that gave me X to be equal 0.075. And if we convert that to a percent, that comes out to be 7.5%. Well, remember what we assigned X to be. We said X was going to be the lithium-6 isotope. So we've just calculated that lithium-6 is 7.5%, which means that lithium-7 has to be 100% minus that, or 92.5%. So that's just another thing we can do with this equation and this math, is actually calculate percents if we happen to know the weighted average. All right, you're going to try some more of these on your own. There's some homework on the back of this sheet. Make sure you do it, and if you have any questions, come by and get some help.